In the world of precision machining, there's this one fundamental challenge that really separates the pros from the amateurs. It's an invisible force that can literally bend steel and destroy your parts before you even realize what's happening. Today, we're diving deep and mastering tool deflection.
Think about it. What is that one thing that every single machinist has to fight against, whether they're a seasoned expert or just starting out? It's a silent saboteur that wrecks your tolerances and can snap an expensive tool in the blink of an eye. Well, that invisible enemy is tool deflection, and today we're going to drag it into the light.
So what is this thing really? Let's pull back the curtain and get a solid handle on what's actually going on with your tool when it's under load.
At its heart, it's pretty simple. Deflection is just the tool bending or flexing when it's under the massive pressure of cutting metal. You know, even the toughest, most rigid material on Earth will bend if you push on it hard enough. And that's exactly what's happening right at the tip of your cutter on a tiny but incredibly critical scale.
You want the perfect way to picture this? Think about a diving board. When no one's on it, it's perfectly flat, right? But as soon as a diver starts walking to the end, their weight makes the board bend down. In our world, the cutting forces are the diver, and your tool, well, that's the diving board. The more force, the more it's going to bend. Simple as that.
Now, understanding the idea is one thing, but being able to spot it out on the shop floor before you've got a bin full of scrap parts, that's a whole other ballgame. So let's talk about the telltale signs that deflection is quietly wrecking your day. There are 3 classic signs you got to watch out for. First, and this is a big one, you're snapping tools left and right. If your tool life is way shorter than it should be, that's a huge red flag. Second, just look at your surface finish. Is it all chattering and rough instead of being nice and smooth? Yep, that's deflection. And third, the most painful sign of all, your parts are just wrong. If you're shooting for a perfect 90-degree wall and you're getting 89.8, you can bet deflection is your culprit.
So how do we fight this thing? Our first, and honestly our most powerful weapon, comes into play before you even press the cycle start button. It's all about controlling one single critical variable, overhang.
Overhang is exactly what it sounds like. It's how much of the tool is sticking out from the tool holder. You know, that distance from where it's being gripped to the very tip that's doing all the work. And let me tell you, this one little measurement is everything. And here's the part you absolutely have to remember. The relationship here isn't one-to-one. It's not linear, it's cubic. Now, what does that mean? It means if you double the overhang, you don't just get double the deflection, you get 8 times as much. A tiny little change in your setup can cause a massive, catastrophic change in performance.
The good news is, the fix is beautifully simple. First, you figure out the absolute shortest length of tool you need sticking out to get the job done without crashing the holder. Got it? Then you choke up on that tool and grip it as deep inside the holder as you possibly can. The more of that shank you've got in the holder, the more support you have, and the more rigid your whole setup becomes. Controlling your overhang is huge, but it's really only half the battle. Your next line of defense is picking the right tool geometry for the specific job you're doing. And a lot of the time, that comes down to a choice between a long flute tool and a long reach tool.
The trade-off here is pretty clear. A long flute tool has those cutting edges running way up its body. It's fantastic if you need to finish a long, seamless wall or clear chips out of a deep slot, but its big weakness, it's just not that rigid. Now, the long reach tool is a different beast entirely. It has short, stubby cutting flutes, but then it's got this long, solid, non-cutting neck. This design makes it way more rigid and absolutely perfect for reaching deep down into a pocket to do some precise work at the bottom.
Okay, time for pro tip. This is a detail that gets to the absolute heart of a tool's strength, and honestly, it's something even a lot of experienced machinists can overlook. We have got to talk about the secret of the core.
So many of us make this mistake. We grab a tool, we see it's a half-inch end mill, and we base all of our ideas about how strong it is on that half-inch number. That right there is a critical error.
Because the real strength, the true rigidity of any tool, doesn't come from its cutting diameter. Nope. It comes from its core diameter, that solid cylinder of material running right down the center of the tool.
And it makes perfect sense when you really think about it, right? Those helical flutes that do such a great job cutting and clearing chips, they're basically just empty space. They're an absence of material. The core is the solid backbone that's left. So a tool with a thicker core is always going to be stronger than a tool with a thinner one, even if they have the exact same cutting diameter. So let's bring this all home. Getting a handle on these fundamentals isn't just about not breaking tools. It's about unlocking a totally new level of precision and efficiency.
It's what really defines those next-gen results we're all after.
Let's recap with a quick checklist. Number 1, keep that overhang as short as humanly possible. Remember that crazy cubic relationship? A little extra length is a lot of extra deflection. Number 2, for rigid cutting in deep pockets, always reach for a long reach tool. That solid neck is your best friend. And number 3, judge a tool's strength by its core, not its cutter diameter. That's its true backbone.
See, mastering tool deflection is more than just a technique. It's a whole new way of thinking. It's about seeing those invisible forces that ultimately decide how your part turns out. Because as materials get tougher and our tolerances get tighter, the future of manufacturing isn't going to belong to the people who can just make a part. It's going to belong to those who can master the physics of the cut.